This video is to teach you about similar figures. At this level we're only interested in what happens to the angles and the lines. This is a B grade topic. Later on we'll be working out what happens to the areas and the volumes. Now, similar in maths doesn't mean the same as it does in everyday English. In everyday English, similar means things are roughly alike. In maths, similar means one of them is an enlargement of the other, so like the shadow of an object. Okay, so they are exactly in the same proportions, it's just one is made bigger than the other. So if two shapes are similar, one is just an enlargement of the other, the angles stay the same. If you think about it, if you looked at the shadow of a square, its angles would still be 90 degrees. And all the lines increase in the same ratio, otherwise the shape wouldn't be in the same proportions. It would have changed shape, so your square might have turned into a rectangle when you projected the shadow. So if that line has tripled, that means all the lines will have got 3 times bigger. These questions are often drawn out in a way that's quite confusing, so the simplest way is always to extract the two shapes and draw them next to each other. So in this example, the two shapes have been drawn on top of each other deliberately to confuse you. So what you've actually got is a little triangle, and then behind it you've got a big triangle drawn to the same angle. So if we extract those two triangles like this, so here's the big triangle, which was 10 centimeters across the base, and we don't know what is its height, and the similar little triangle here, which was 6 centimeters along the base and 2 centimeters high. Now it's easy to see what the increase has been, what the enlargement has been. So if I do 10 divided by 6, I can see that the short lengths have all been times by 1 2/3 to get to the long lengths, and because all the lengths have to increase in the same proportion, that means that the height must have been times by 1 2/3. So if I work that out, the height must have been 3.3. Now this next one is a very typical example, and it's a good demonstration of why it's a good thing to draw the two triangles out in the correct alignment. So at the moment, the smaller one has been flipped around compared with the bigger one. So if we work out which angles compare with which, because we've got a Z angle here, we know that that angle compares with that one. And we've got another Z angle here, so we know that that angle is the same as that one. And because we've got two opposite angles here, we know that these are the same. So if I redraw this so that these two triangles are in the same alignment as each other, it becomes much easier to see which length corresponds with which length. So if I imagine taking this one and spinning it around so that it's facing the same way as this one, then the two triangles would look like this. So I've taken this one and spun it around so that just like this one, that angle is at the top in both cases, that angle is at the bottom in both cases, and that angle is facing to the right. So the two triangles are in the same alignment. You could imagine now shining a light here, for example, and this one being the shadow of this one. So now that I know which sides in the small one correspond with which sides in the big one, it's very easy to see that the scale of the enlargement is times 3. So if that side has been times by 3, this side must be times by 3 as well. So the x must have been 9 centimeters.